All right, welcome to section 4.5. We are going to be putting all of our work together, and we're going to be sketching some really complicated curves. So we're going to be doing the summary of curve sketching. And again, sketching some really interesting curves. So really what we're going to be doing in this section is we're going to be able to figure out how to sketch functions by hand. Okay, and this is a multiple step process. So before we even look at an example, we're going to go through all of the steps. So what does it mean to sketch a function? And what should we include when we sketch a function? All right, so the first thing we should be aware of is the domain. Look for any domain restrictions, whether it be a hole in the graph, whether it be an asymptote, anything like that. The next thing we're interested in is intercepts. And we know for intercepts, we know we have a y-intercept at f of 0. All right, and then we have x-intercepts when the function's equal to 0. And we're going to want to include those whenever we can. We can almost always include the y-intercept because plugging in a 0 is easy. But sometimes finding the x-intercept is difficult. So as far as the x-intercept goes, we'll make a little side note. If it's truly difficult to find, and sometimes it is because we know how crazy these functions can get, you can sometimes skip the x-intercepts. Okay. The other thing with curve sketching, we can take advantage of symmetry. And we have a couple different types of symmetry. We know a function can be even or odd. If a function is even, it means when we plug in negative x, we just get back our original function, f of x. And this is called an even function. And even functions, do you remember what kind of type or what type of symmetry they have? They are symmetric about the y-axis. Okay, so we're going to be mindful of that symmetry when sketching our curve. Some examples of even functions. Well, y equals x squared is an example of an even function. Notice if we were to plug in negative x, well, negative numbers squared are positive numbers, so we would get back our original function. And we also see we have this nice symmetry going down the middle, that y-axis, okay? And again, if we were to plug in negative x, we would get right back to our original function, okay? So that's why it's even, those two reasons. Other examples, something similar shape is the absolute value function. That's also an even function. It's also symmetric about the y-axis. And another one from trig is the cosine function. Right, that's one period, and then on the other side, it looks exactly the same. And we know from our trig class that if we were to plug in negative x into cosine, we would get x. Okay, and we can see that right here too. If we were to plug in negative x, whoops, should be more symmetrical, I'll just make a big dot, we would get back the same value at positive x, okay? So we get a nice nice symmetry about that y-axis. Okay, so the cosine function is also an even function. Okay, the other type is an odd function. And it's an odd function if we plug in negative x and we get the opposite of our original function. And that's our odd function. And odd functions are symmetric about the origin. And really what that means, symmetric about the origin, we have a reflection twice across the y-axis and across the x-axis. Okay, so some examples of this. We'll do 2. Y equals x cubed. Let me draw this a little bit better. Because again, notice if we were to plug in negative x, we would get back negative x cubed, which is negative y, right? So y of negative x, in this case, brought us negative y. All right, and this graph is symmetric about the origin. And again, what that means, if we were to have an xy on the graph, being symmetric about the origin, we would reflect it across the x-axis and we would reflect it across the y-axis. So that's what it means to be reflected or symmetric about the origin. Another example is our sine function. Again, I should have, there we go. Sine is an odd function. Again, when we plug in negative x, we know from trig that's going to get us negative sine. Okay, so here's one period of sine, and we can extend it forever, as we know. And it's an odd function. If we were to have an xy, I'll just go right here. On our sine graph, we would reflect it once across the x-axis, once across the y-axis, and we see negative x, negative y is also on the graph. So it's an odd function. So all of these types of symmetry, both these types of symmetries, we're going to have to be mindful of when we do our curve sketching. We're going to want to show that symmetry in our sketch. The last type of symmetry is periodic symmetry. All right, so we know the sine and the cosine are periodic functions, and they repeat, you know, every 2 pi period, for instance. Okay, so that's called a periodic function, and if we have that type of repetition, we have to show that in our curve sketch. So again, this would be considered a periodic function. In this case, it repeats every p. So we would say with period p. Okay, so in this type of symmetry, it's more of a horizontal or a translation symmetry. And I said horizontal, it doesn't necessarily have to be horizontal, but it's a translation symmetry. Okay, so for instance, we know that sine of x plus 2 pi is equal to sine of x, right? So the period is 2 pi, that p. So when we are graphing a sine function, we're going to want to show that translation symmetry. All right, so, and how it repeats every 2 pi. Okay, so something like that. That's something we'd want to show in our curve sketch. Okay, so the next part, we're on D. What else do we want to show in our curve sketch? Any asymptotes, horizontal or vertical. Okay, so remember for the horizontal asymptotes happen at the infinities as x goes to positive and negative infinity. So to find the asymptotes of a function, you would have to look at the limit as x goes to positive and negative infinity. All right, and it won't always be asymptotic. But, if the limit is equal to L, remember the horizontal asymptote would be y equals L. Okay, and that's a horizontal line. We also have vertical asymptotes. And vertical asymptotes happen where we have discontinuities. So, for instance, in our rational function, anything that makes the denominator 0 could potentially be a vertical asymptote. The calculus definition is we can go from the right or the left of a value a, and if we go off to plus or minus infinity, that's going to be a vertical asymptote. Okay, so to the right of a or to the left of a. And in that case, if this holds true, then the equation of the asymptote is a vertical line x equals a. Okay, so here we have our horizontal asymptote, potential, not guaranteed, and we have our vertical asymptote. You can just draw yourself, whoops, let me draw a dotted line. Dotted line to help you remember. Okay, and then another type of asymptote you guys might have heard before, but we haven't talked about it yet, is a slant asymptote. And we'll talk about this one later. All right, there's a couple cases, but we'll focus on that later. All right, so what's next? Now we're going to get into the things we learned in Chapter 4. So we're going to want to include the intervals of increase and decrease. The ID test. So that's when we find the derivative and we figure out where the derivative is positive and negative. We did that in Chapter 4. And then we're going to want to use the local min and max, or find the local mins and maxes. And we have two ways of doing that. We can use the first derivative test or the second derivative test. All right, and we'll review that in a second. And then finally, we want to look at the concavity and any inflection points. Okay, and we do that by using the double derivative. And it's not called the second derivative test, but we use the second derivative to give us information about the concavity. And then finally, once you have all of those pieces of information, part H is actually sketching the curve. And we sketch the curve using parts A through parts G, the ones we just outlined above. Okay? So let's put all of these together. Let's try to sketch a crazy looking function. Okay. And we're going to follow those steps A through H. So the first step is figure out your domain. All right, so as far as domain goes, the only thing that would be a problem, right? And again, domain restrictions happen with rational functions. We don't want the denominator to be 0. They happen with logarithms. The argument has to be positive. They happen with even roots because the argument has to be greater than or equal to 0. So in this case, we have an even root. We have the square root. And so we're going to want x squared plus x to be greater than or equal to 0. Okay, so we have to solve this. This is a quadratic inequality. So how we solve quadratic inequalities, we make one side 0, and we factor. Okay, that tells us, once we factor it, this tells us where the zeros are. So the zeros of this inequality are x equals 0 and x equals -1. Those two numbers will make that inequality 0. Okay, so from the -1, or with using the -1, -0, positives, -1 and 0, we have to figure out where x squared plus x is above the line. Okay, and we know we can use test points. We've seen that before. So for instance, plug in -2, see if we're positive or negative. Plug in -1/2, see if we're positive or negative. Plug in +1, see if we're positive or negative. But I know the basic shape of x squared plus x, that's a parabola, and the leading term is positive. So I know that the parabola is going to look something like this. That's just how it's going to fit, right? Fitting the shape with the two zeros, we look like this. So we're going to be fulfilling this inequality when our parabola is positive, when it's greater than or equal to 0. And then that's going to be our domain, because again, we want to make sure x squared plus x is greater than or equal to 0, and it's going to be greater than or equal to 0 on those intervals, -∞ to -1 and 0 to infinity. And we're including because we're allowed to be 0. Okay, so again, the domain is this. So we're going to have a gap in our graph between -1 and 0, and there's just not going to be any graph above or below. It's going to just be blank space above and below. Okay. So what's next? Part B is the intercepts. All right, so part B, we're going to be finding the intercepts. And there's the y and the x-intercepts to consider. So let's do the y-intercept first, because that's the easiest. We just plug in 0. So y is 0. What do we have? We have the square root of x squared plus x minus x. And if we plug in the 0, it's going to be 0 plus 0, which is 0, minus 0 is 0. So y of 0 is going to give us 0. Excellent. So let's talk about the x-intercepts now, or x-intercept, we don't know. So that's when our function is equal to 0. Okay, so how we solve equations with root symbols, if you remember, we isolate the square root. So let's add x to both sides. And then we square, or if it was the cubed root, we would cubed, right? Whatever the index is, that's how we raise it to. So since it's a square root, we're going to square it. That's going to get rid of the square root. And now that's equal to x squared. Okay. So we solved this. So let's subtract x squared from both sides. We're going to get 0. And so it looks like we have one x-intercept and it's 0. The x-intercept and the y-intercept are the same. So it's going to happen at the point 0, 0. So we're going to want to make sure we include that on our graph. Okay, let's talk about symmetry. That's letter C. Symmetry. Okay, so how we figure out symmetry is we plug in negative x to see if it looks like, to see where it gets us. Are we going to get exactly our function back? Are we going to get a new function? The opposite of our old function? We don't know. So let's go ahead and start. We're going to plug in negative x. Our function is x squared, or input squared, plus the input minus the input. Okay? Here's our function again. Okay? So if we simplify, we're going to get x squared minus x plus x. Okay, and then this is neither, let's see, y of x is equal to x squared, square root of x squared plus x minus x. So that's not it. And then negative y of x is negative square root of x squared plus x. And then minus is plus, okay? And notice that this expression is not this, it's not y of x, and it's not negative y of x. So what can we conclude? There's no symmetry, okay? And definitely no translation symmetry, because our function values aren't going to repeat at some point like our trig functions do. We're not racing around a circle like our trig functions. All right, so there you go. No symmetry for part C. And then D, we're going to be figuring out our asymptotes. And we have two different kinds. The vertical asymptotes that happen with domain restrictions. And then we have horizontal asymptotes. In this case, let me go back to the domain. Our domain is a closed interval. Okay, and then notice, like at 0, if we were to plug in 0, we would get 0. If we were to plug in negative 1, we would get, let's see, if we plug in negative 1, we get 1 minus 1, that's 0, minus negative 1. We would get positive 1, okay? So we don't have any asymptotes at the endpoints of our domain. Excuse me. So that's telling us there's no vertical asymptotes. Because again, vertical asymptotes occur with domain restrictions where we're not continuous. So let's figure out if we have any horizontal asymptotes. And horizontal asymptotes happen at the as x goes to the infinities. Okay, so let's look at the limit as x goes to positive infinity of our function. Okay, and remember our strategy with limits at infinity, we like to divide out by the highest power in the denominator. That's one of our strategies, but we don't have a denominator. So we do have a square root. So we do have this strategy where we can multiply by the conjugate. That's going all the way back to chapter 2. Chapter 2 in limit strategies. And whatever we do the top, we got to do the bottom. Okay, and the reason why we do that is now when we multiply, right, this is an a minus b, a plus b situation, the top's going to be a squared minus b squared. And square root squared cancels out that square root. So here's your a squared minus b squared. In this case, it's going to be x squared. All right, and then on the bottom, we have that in green. All right, so let's see, the x squareds and the x squared cancel. And now I'm looking, what's the highest power in the denominator? Well, I see an x squared in there, but it's an x squared underneath the square root. So really that's just behaving as x. So we're going to come through and we're going to divide everything by x. And then again, when we put it inside the square root, if x is going to positive infinity, x is equal to the square root of x squared. Okay, so that's where we're going with that. So what's gonna happen? Let's clean this up a little bit. In the top, we have 1. In the bottom, 1 plus 1 over x, and then plus 1, okay? And now, the only thing that's affected as x goes to infinity is 1 over x. And we can, go about it 2 different ways. We can remember what the graph of 1 over x looks like. And as x goes to infinity, 1 over x goes to 0. Alternatively, we have this property that says, I think it's a power too. If we have 1 over infinity as a limit, that just equals 0. Okay, so again, that's all from chapter 2. A nice review, bringing everything all together. Whoops. Remember, if I'm taking the limit, I don't need to write the limit, or if I took the limit, I don't need to write it. So we're looking at this. All right, so what's that going to simplify? 1 over 1 plus 1 is 1/2. Okay, so y equals 1/2 is an asymptote. It's a horizontal asymptote. So we're going to want to make sure we include that in our graph. Okay, and then remember that's as x goes to positive infinity. Let's switch colors and see what happens when x goes to negative infinity. Oops. Do orange. And it's going to be the same process for the most part, but it's going to be a little bit different because we're going to negative infinity now. Forgot my original function, minus x. Okay, so same thing as before. We're going to have that same strategy where we multiply top and bottom by the conjugate for reasons we've already discussed. Okay. And we get that a squared minus b squared scenario in the top. So far this is exactly the same. All right, and then right here is where it's going to change. So I'm just going to clean up the top. I'm going to get rid of x squared minus x squared. And now it's time to divide each term by the highest power in the denominator. And again, it's x. Okay, so part of this process is similar. Okay, so that's the same. But now we have to take x and give it a square root. Oh my goodness. Let's try this again. X and give it a square root, right? So remember, square roots and squares cancel each other. Okay, so we know this. But the square root of x squared is a positive number. That's how square roots are defined. Square roots give us positive numbers. But x is going to negative infinity. So x needs to be a negative number. So we're going to have to put a negative sign in front of that square root of x squared. Okay? So when we bring the x into the square root, we're going to bring it in as x squared, and we're also going to need a negative sign. All right. So again, we covered that a lot. We did that a lot in chapter 2. So what are we left with? So on the bottom, we have negative square root of 1 plus 1 over x plus 1, okay? And then again, as x goes to negative infinity, 1 over x will go to 0. All right, and now this time in the bottom, we're going to have negative 1 plus 1 is 0. Okay, and so that's going to take us, so infinity, right? It's going to be either positive or negative infinity. We'll see based on our graph. But as x goes to negative infinity, our function's just also going to go to negative or positive infinity. Let me look at our graph really quick. Yeah, and I think if anything, it will be positive. Oh wait, here we are. It will be positive because this number is going to be most likely bigger than that, but we'll see, okay? So in this case, we only have one horizontal asymptote, and that's y equals 1/2, okay? And then that's as x goes to positive infinity. So we'll have to remember that for our sketch. Now we don't have a horizontal asymptote when we go to negative infinity. Okay. Next up, we're going to be looking at the ID test. Okay, so increasing and decreasing test. How we do their increasing and decreasing test is first we have to take the derivative. Okay, so think of that square root as a 1/2 exponent. All right, so then y prime, first we're going to take the derivative of the outside function. 1/2 minus 1 is negative 1/2. And then we're going to multiply it by the derivative of our inside function. Okay, so that's the derivative of this first part. And then the derivative of negative x is minus 1. Okay, so I'm going to clean that up a little bit. Let's see, in this first term, only the 2x plus 1 is in the numerator. And then everything else is in the denominator. That negative exponent sends it downstairs, right? And then we have the minus 1. Okay, so now we have to figure out where this function is positive and where this function is negative. And if you recall, the first step to the ID test is finding out where the critical numbers are. So remember, for the critical numbers, we have to determine where y prime is 0 or where y prime is undefined. That's what the critical numbers are. So let's start with the zeros. So let's take that 2x plus 1 over that denominator, 2 root x squared plus x. Minus 1 equals 0. I see that radical sign in the denominator, so I know I'm going to have to isolate that root and then square both sides. That's how we deal with square roots in equations. So how am I going to do that? Well, I think I'm going to add 1 to both sides. Do a little cross multiplication. So this way. All right, and then I'm just going to square it. So square both sides. That's your strategy for these square root problems. So I have 1, 2, 3 factors here. So we have to make sure we square all 3 factors. So we're going to be looking at 2x plus 1 squared. 2 squared is 4. And now square root and squares cancel each other. So we're looking at x squared plus x. Okay. So let's clean this up. So 2x plus 1 squared, that's like 2x plus 1 times 2x plus 1. So you can FOIL it, or you can remember the formula if this is a plus b all squared. The formula for that is a squared plus 2ab plus b squared. All right, and on the right, let's distribute that 4. All right, and let's see what happens. 4x squared is going to cancel. 4x will cancel. And we're left with 1 equals 0, right? If everything's canceling, we're just left with a 0. So what does that tell us? Well, it tells us that there's no solution to y prime equals 0. So there's no zeros of f prime. So if we're a critical number, we're going to have to be in the second case where y prime is undefined. Okay? And if you look at our y prime, here's our y prime, we have 2 things. We have a denominator and we have a square root. Okay? So that means that this part right here, x squared, square root of x squared plus x, first of all, if we're undefined, because that's what we're trying to find, remember, where are we? Here we go. Where y prime is undefined, that would happen when this is equal to 0 and when x squared plus x is negative. That would tell us that we're undefined because we can't have a 0 denominator, we can't have a negative square root. So I'm going to take that, that's right, good note. So y prime is undefined when x squared plus x is negative and 0. Okay, so something like that. Okay, and we solved this already, right? We already figured out the zeros. We did something similar for the domain, right? We already figured out the zeros and we already figured out the shape. This is where our function is negative. So where x squared plus x is 0 and negative is between -1 and 0. Okay, so it's out of the domain. Okay, so let's kind of take a step back and figure out what we're working with. So we're working with the derivative, right? Yes, we're undefined between these points. We are undefined. We're out of the domain. So it's kind of hard to figure out what happens around these numerous, infinitely many number critical values. But think about how the function's behaving. Our derivative is going to change sign before or after the gap. Okay? There's no zeros of f prime. We're only undefined when we're out of the domain. So the only time f prime can have a sign change from negative to positive or positive to negative is when we leap over the domain restriction. Okay, so that's a little bit different. So we can find some test points, maybe -2 and -1. Where's f prime again? It's a little complicated. Okay, so here's our f prime. So complicated, right? I'm going to write it up here so I don't have to keep referencing it. All right, so let's put in our test point, Okay, so on the top, we're going to get like -4 plus 1. It's -3. And on the bottom, we're going to get 2, and then 4 minus 2, and the radicand is going to be 2, right? And then -1. Okay, so we have, let's see, this is a -3, right? This is going to be a positive number. So this whole thing is negative. And negative number -1 is just more negative. So here, our derivative is going to be negative. So what does that mean? Well, according to our ID test, if our derivative is negative, that means our original function y is decreasing. And then it's going to be on the interval -infinity to -1. All right, we can't go to 1. -1 is undefined. Okay, so what else do we have to test out now? Our next test point is this interval. We're going to plug in a 1. So y prime of 1. Wait, did I do 1? Yeah. What I'm going to do, let me do 2. Just to have nice symmetry. It doesn't matter. You could have done other. Okay, and so what do we have? So in the top, we have a 5, and then 2 square root of 4 plus 2 is 6, and then -1. And then let's see. Well, this is a little interesting. We could definitely use our calculator to figure out if this is positive or negative. And I think we would have to. At best, we can estimate 6, root 6. Remember this trick, how we look between two perfect squares? And then if we take the square root, now we know root 6 is between 2 and 3. And that's a tricky one, because if it's closer to 2, then that's like 4-ish. So 5 over 4-ish is more than 1. This is positive, right? But then if it's closer to 3, then 2 times 3 is 6. 5 over 6 is, smaller than 1. Now it's negative. So I'm actually going to use a calculator on that. That one's a little bit tricky to do in our head, or even scratch work. And then using your calculator, plugging this in, it's actually positive. So there you go. So that tells us that the derivative is positive on 0 to infinity. So that means y is increasing, the original function is increasing on that interval, which was 0 to infinity. Okay, so again, we can use that to sketch out our curve. Okay, so moving on. We're on part F. Now that we have that derivative set up, we can find all the local mins and max. Again, how we do that is the first derivative test. And there's really no local mins and local maxes, right? Because our critical, here we go, there's no zeros of f prime. So there's no local min and local max. So let's just kind of write out that thought process. No zeros of the derivative, so there's no critical numbers per se. So, we're going to see that there's no local mins or local maxes. What we do have is a big domain restriction at -1 and 0. We know that y is decreasing from -infinity to -1, so the function is decreasing. And then from 0 to infinity, we're increasing. Okay, so if anything, this is telling us what the it looks like absolute mins and maxes could be, or those are behaving as the local mins and local maxes. All right, so just based on the derivative, we know it's decreasing on this interval. We know it's increasing on that interval. So -1, y of -1, and 0, y of 0, just visually looking at our graph, these are kind of behaving as our local mins. All right, and we can plug in those values to our original function. And we kind of did that briefly. Okay, and we're looking at something like this. So those are behaving as the local mins. All right, so we'll have to make sure we include these points on our graph. What's next? Almost done. We have one more thing to look at, and then we can put all of these pieces together. And we're going to find the concavity. And we find the concavity by looking at the double derivative. Okay, so that's going to be fun. All right, so here's our derivative, and now we have to take the double derivative. So we're going to have to use the quotient rule. So I'll write that in blue so it sticks out for us. So the derivative of the top is just 2. Okay, minus the derivative of the bottom. Okay, and let's see. We can have the 2 here, and then we'll just take the derivative of this, and then multiply it by 2 later. And we've done this before. It's the chain rule. So we can do 1/2 times x squared plus x, the negative 1/2, now times the inside function 2x plus 1. All right, and then we're going to divide that by the bottom squared. So that's our quotient rule. And then the derivative of -1 is 0. So we can just stick with what we have in blue. Okay, let's do some cleanup. I'll use a different color. So here, this is going to be 4. And then 2 times 1/2 is 1. And then this will be on the top. 2x plus 1 is on the top. And then we have the square root of x squared plus x on the bottom. Okay, and then on the denominator, let's see, 2 squared is 4, x squared plus x, again, square root and squares cancel each other out. Squared plus x. All right, that's crazy, right? We're gonna want to figure out where the double derivative is positive and negative, right? That tells us about the concavity. So to figure out where it's positive and negative, again, we're gonna want to find the zeros first. So since I want to do the zeros, I'm going to clean this up a little bit because I don't want to work with complex fractions. So I'm going to multiply top and bottom by the numerator, clear the numerators. All right, so I'm going to multiply 1, 2, 3 terms by this. Okay, so root x squared plus x times root x squared plus x. Square root of x squared plus x. I don't think I'm saying that right. It's a lot to say. But the square roots cancel. And then make sure you put parentheses around 2x plus 1. We're going to subtract the whole numerator, not just the first term. And in the bottom, we'll have the square root of x squared plus x. All right. And then where are we at? So we're going to have let's see. Hold on one second. And And I think I made a mistake. Did you guys catch it? I hate that. So let's go back up here and we'll just add it. I just saw in my notes that I made a mistake and now I caught it. When we were doing the quotient rule, this is just the derivative of the bottom function. We also have to add 2x plus 1. Sorry about that. I just got so excited. And then this is actually then 2x plus 1 squared. All right, so an easy modification. Hopefully it didn't throw you guys off too much. All right, so now we're going to clean everything up. Distribute that 4. Do 2x plus 1 all squared. And then on the bottom. And then you can leave this as that, as it is. Or you can add, 1 plus 1/2 to the base x squared plus x, because that's what it is. But it doesn't matter. Whatever floats your boat. And then what do we have? So in the top, 4x squared minus 4x, 4x minus 4x, and then -1. So we're left with -1 over 4 times x squared plus x to the 3/2. And then this is our double derivative. That's what, that was a long ride, right? That's our double derivative. So notice that the numerator is a constant. So since the numerator is a constant, there's again no zeros of our double derivative. Double derivative has no zeros. And then again, the derivative is going to be undefined, just as it was before, when the bottom is negative or 0. And that's going to happen at between -1 and 0, right? All those numbers in between, but the only numbers in the domain are 0 and -1, okay? So if we have a concavity change, it's going to happen at -1 and 0. So let's kind of map that out. Remember, it's important to label your number lines because we go through so many, right? We look at the first derivative, then the second derivative, and then we graph the function. So it's always important to know where we are. Remember, we're not allowed to go in this zone. That's the domain restriction. So f double prime could change signs over that domain restriction. So we got to figure out the sign of the double derivative in those two OK zones in the domain. And then we can determine if it's concave up or concave down. Okay, so let's look at our double derivative. The bottom is positive. Excuse me. The top is positive. X squared plus x to the 3/2, because of the domain restrictions, is always going to be positive. So this whole thing is going to be positive. But there's a negative sign. So the double derivative is always negative, just based on how the function works. We don't even need to do test points because it's a positive number that's negative. That's always going to be a negative number. So we know that this whole function is going to be concave. What happens when the double derivative is negative? Concave downward. And then that looks like your sad face. It's like a bowl upside down. Okay, and then on that interval, excluding those endpoints. Okay, so we have a ton of information. And we're ready for part, goodness, are we on part H? We're going to graph. Okay, so we know that there's a domain restriction between -1 and 0. So you don't have to include this on your graph, but we're not going to have any graph in this zone. We're not going to have any graph in that zone. And there's a whole bunch of information besides just the domain. So let me scroll up, not too fast so I don't give you a headache. Look at all this work we had to do. So that's part A. We have this domain restriction between -1 and 0. Intercepts. We're going to include 0, 0 on our graph. Okay. No symmetry, no vertical asymptotes, but we do have a positive asymptote. As x goes to positive infinity, our horizontal asymptote is y equals 1/2. So we'll put that on the graph as well. ID test. Here we go. Decreasing between -1 and -infinity, increasing on 0 to infinity. Local mins and maxes, we just have these 2 points behaving like the local mins and maxes at the endpoints of the domain. So we're going to make sure -1, 1 is on the graph and 0, 0. And then finally, concavity, we just discovered that we're concave down on the domain. Okay, so again, some important points is we have 0, 0. Let me try to get the 1. And then remember what happens at 1/2? Y equals 1/2 is our asymptote, horizontal asymptote. So we'll make sure that's on the graph. What else? We had the point -1, 1 on the graph. That's behaving as a local min. And some other things we know from -infinity to -1, we're decreasing and then concave down. And then 0 to infinity, we're increasing and again concave down. All right, so let's see then what that looks like. So here we have to be, our graph is decreasing, okay, and we're concave down. So we're gonna be looking something like this. Skip the domain restriction and now we're here. And we're increasing and concave down, okay? And as we go to positive infinity, we have to tend towards this line. So we can do something like that. And that's that. So again, this is the graph of the square root of x squared plus x. And then, whoops. And then was it minus x or plus x? Again, it happened so long ago. It was minus x. All right, and we were able to graph it using that multiple step process. So in part 2, you guys are going to practice graphing 1 as well.